early version, you can try to plug it in.
Quite a few.
So thanks for meeting us again after lunch, and we have another interesting session about to begin. And the first talk is about the ML as a tactic language yet again, right? From where it once started to well, using it again as a tactic language. The speaker will be Guido Martínez, and yeah, this is the work of the whole star team as far as I can understand. So yeah.
So hi everyone. So yes, this is work by the star team, in particular by these 13 people that are part of this mission. So yes, I'm going to tell you a bit about MetaStar, which is the tactics and metaprogramming language for a star, and we're doing this calling it ML tactic language again, because MetaStar is also a subset of a star, which is an ML language. There's going to be an overview of the thing. There's many things to understand, and going into detail. I really don't think I can go into detail and stay in like the 20-25 minutes that I have. So very, very quickly for a start, this is like the one slide intro to a start. It's a dependently typed functional language. It's primitively effectful. You can program with effectful computations and reason about their behavior alongside the same language. It's similar to ML. It's high order, polymorphic, strict, safe, a strict mean called value. You can declare very expressive specifications over very effectful terms. I would say almost arbitrary specifications. And one of the things that makes it stand out as well is that it has a proof relevant logic, if that's a good name. These effectful computations are specified by insider types of WP calculus, where the proofs are never materialized, or not necessarily materialized in terms. It's mostly at the logical level, things just work, as the example just now. And that's one of the features that allows it to discharge all these things to an SMT solver without having to reconstruct the term back into the language. So a quick example. This is a stateful function in a star. We have the increment function, takes a reference to an int, and increases by 1. Stay with me, this is complicated. And now we're going to call it, we have a reference, we have 1, increase it, read it again, and we have this assertion here that states that the value we get is 2. So the way this thing type checks and verifies in a star is using types and specifications for the primitive things we see here, like assignment, allocation, and reading reference, which are these things right here. And they work by a WP calculus, weakest preconditions in case they say what the name. But things are really shaky. They are specifications of terms that take a post condition and turn it into a precondition of a stateful computation. So if I want to know, I have a stateful computation and I want to say, okay, when I run it at the end, I want to get something that satisfies this, WP tells me, okay, you need to start it in a state that satisfies this. It's basically a CPS of spec. And we have these guys, these are all specified in the Stockholm library, and they say, well, it's hard to read because of this CPSing, but this says, when you read a reference, it has to be in the initial heap, and you're going to get the same heap, so going to change, and the value of the reference as a result. So using these guys, I start to compute a verification condition for this formula, and we need to prove that 2 equals 2, so we get that beautiful formula, right? No, we get this thing. And this is what we need to prove and send to the SMT solver. And this includes basically all of the control flow of the program, all of the, some of these things are abbreviations actually, and there's some invariants in the heap. But we get a thing that's a mess. And it's kind of saying that 2 is equal to 2 in a very roundabout way. And of course also that, that the reference is slide, but it's very read it, so I allocate and I call this an remain slide. All of those things are actually in here as well. But at a glance, if I try to prove this, if I, as a human, come here and say, oh, I'm going to instantiate these quantifiers and do the proof, that's going to be a pain. So what's the way we do proofs in FSTAR? It's certainly not taking those things and putting them into COG and using our tactics. The usual way, up to now, is the user writes a program, like the one we saw before. FSTAR computes a verification condition, like this monster, and sends it to the SMT solver, usually C3. Right. So all user input, all of the way you interact with the tool, happens before the VCs are generated. You write program text, you get a VC, and it just goes straight to the SMT solver. And this is called autoactive verification, and some people call it like that. When all user input happens before the VCs are out there, you don't get to see them and tweak them. So what happens when the solver fails? What happens when I write a program and the solver doesn't see that it is actually correct and satisfies the spec? So let's say we want to prove a lemma. Lemmas are really just functions with a post condition. Let's say I want to prove this. It's a quite basic fact about modulus and subtraction for integers. And what we hope to write is simply just this. The proof of this is trivial. Just send it to the SMT solver. But SMT solvers are really bad about doing this kind of thing, like modular arithmetic in particular. So then what do? You write this, of course. I'm sure everyone is thinking of this, right? And this is actual source code from the library, from someone who needed to write this proof, and this was the only way to do it. You basically need to call these three lemmas, which bring into scope the things that you need to prove this, or that you need, that you can use to prove it without really going into modular arithmetic. And the SMT solver can just connect the dots easily. And these assertions are mostly like sanity checks that, okay, they're not failing, so I'm going the right path. This doesn't really scale. This is a heroic effort for such a simple lemma. So this is why we need tactics. Some proofs are out of the solver scope. The solver is just not going to prove it by itself. And not of the programmer sanity scope. They're just going to go nuts to prove this. So we need a tactics engine, and this is what basically describing. We want a way to tweak group obligations before sending it to the SMT and having more interactive verification. And here it has a work in progress marker because we don't really, it's not like we compute the VCs and then write the tactics, but we embed them into the terms. It's not, I mean, when I want to say it's not as interactive as COG, but it's not like you're shooting lines as we saw before. I'm going to give you an example later. So the new modus operandi is you write a program that sort of computes the VC, then some tactics apply to the verification condition, and then you get many smaller verification conditions that we send to the SMT. If any, maybe not. Maybe your tactics just really prove it. But actually, these two steps are the two middle steps are kind of intertwined. We can the tactics can help in computing the VC itself, not only discharging it. I will briefly describe that later, not very much. So, how do we actually use tactics from FSTAR in the language? We have 4 entry points, at least, what I'm describing. The first one is when I have an assertion inside a particular program, like the one we saw that v equals 2, and I want to prove it by a tactic tau over there. We also have the way to catch an entire VC. So in this first style, I'm proving a small proposition within a context, and here I'm just proving some huge verification condition that I don't know what it's going to be about. And I'm going to send a tactic or a meta program to tweak it, and it's possibly going to be something more hammer-like to go and do something automatically over the format. And we also use the same engine for doing meta programming, like generating terms and definitions out of thin air without having to write them down. The two ways we have to do that is this underscore by tau, where it's going to run the tactic and try to find a term to fill this on the type expected by the program at this point. Finally, to generate like chunks of top-level definitions all at once, we have this directive splice, it's a top-level thing that runs this and generates a list of definitions. It just spliced into the program. And formally, what this is doing is the way the tactics of the metaprogramming start is, in this case, within a context gamma representing like this program point, we need to give a term of type squash feet. I'm sorry, this is type, and we can read squash as proof of. SR has a weird logic. I'm not going to go. In this case, it's pretty much the same, except that BC is the proposition that says that this guy over here, the three dots, actually have type C, have computation type C. So it's usually an unpredictable thing. You don't really know the shape of BC. Well, here it's exactly phi in Europe. Metaprogramming term simply, okay, generate something of type type, where type is the expected type of this program chunk. And splicing is a bit different. Splicing actually, you run it, the context is empty, the local context is empty, this is the top level thing. And you need to generate the list of syntactic representations of definitions, which are just going to be run into the compiler, type checked as if the user had written it. So, a bit more detail on those entry points. How do you use syntactic insertion? Here, a small example, we have some function f and some assertion within it, g of xy is z, whatever. And if we write this as is, then it's probably going to be encoded within the verification condition and within the huge verification condition. And the SMT swap is going to have to prove it, among other things. But maybe we know that this just reduces to the same thing. So we can, instead of an assert, we assert by and write a tactic here. And the things, the first one basically takes the goal and normalizes it. The second one is a canonicalizer that we wrote. Trying to keep it not too much detail. And TRFL says if I have equality, then the two sides will unify, and this is circles, which is just a circle like that. Metaprogramming is similar by the hooks that I mentioned before. So here we're generating the term 1, amazing. Second, we're generating 1 plus 2. This is actually generating the syntax 1 plus 2, not the number 3. That's normalized. And do some more fancy things like metaprogramming the huge Fibonacci number. And splicing is actually useful for not having to write a bunch of boilerplate code, like for example a printer for this type. Instead of putting it by hand, we have a type called empty printer that does some introspection on this type and generates a big top-level definition. This one. In some more cases, that just gets spliced into the program, and we don't have to write it ourselves. So it's a way of like the power of that I can show in Haskell or some PPAs that I can in a camel. We just do it by a metaprogramming as well. And one of the curious things about a star and its and the way it does program verification is that the control flow matters, right, in trying to verify. So for instance, if the user writes this with or without the assert, this is a function that it's saying takes an integer, returns an integer, and whatever you give it, it's going to give you something bigger. And just for the sake of the example, I could just add one. For the sake of the example, let's say I'm going to check that if the integer is positive, then I'm just going to do m plus n, and I know it's greater. If it's negative, this does not hold, right? So you need the assumption that you're in this branch of the if to prove this fact. And syntactically, if you were to say, I want to syntactically build a proof of m plus n greater than n here, using the things I have in the lexical scope, it's just not possible. There's no binder in your context that says that n is greater than 0. And it's only at the level of the logic, at the level of the computation. And this works in both in SR and meta-SR, because in the BC that we compute, there is an assumption that n is greater than 0. And when we run the tactics engine and this particular assertion, we get such a hypothesis in the current context. So the way we do that is to take those huge VCs and extract the thing we want out of it is we have this thing called this marker called width tactic, which is really just a glorified American identity function. It just ignores the tactic. Logically, it really does nothing. It's really just equal to phi. And assert phi by tau is actually user defined. There's nothing special about it, and it has width tactic tau phi as a precondition, and it ensures phi. So this is the same as an assertion, as a normal assertion. The normal assertion simply does not have a tactic here, and this causes it to be that we get in the huge verification condition that we show, we have some things marked with tactic something, and we're going to extract those away into separate goals that we can process. The way it's working is we have to prove some, in some context gamma, some formula C that has a phi that we want to split out of it. Right? This is within, within the scope of some quantifiers, some for all, some implications, and the phi is in the scope of all that. We want to extract it away. What you do is replace this thing by t, by true, and we now prove phi in this gamma extended by all of the quantifiers that scope over this whole of C. And doing just this is a meta theorem of logic, and basically any logic is not really what to do. And we know now we have to prove only phi in a separate context, so we know exactly what we need to do. Wow, time is flying. So I'm going to go very quickly, I guess. So okay, now this skeleton, we're just going to send this to the SPD solver. This thing we need to prove. We're going to run the tactic fully. We're going to get a new set of goals that we're going to send to the SPD solver individually. And we only do this actually when we have a huge verification condition. We might have width tactic in many places. We just do this for the positive positions, everything that's under, basically only to the right of implications and quantifiers. On the left, they're hypotheses, so we don't need to do anything, we just leave them as is. I'm going to go much into this, but one of the key things in XR is that typing is undecidable. If I give you a term and a type, and I ask you, does this term have this type? You cannot automatically know that. There's no decision procedure for it. Which is basically a consequence of the fact that proofs are not materialized. So metas and these primitives actually are not built in syntax as in, say, coq, which is then retype check, but are actually scripting a typing derivation for whatever thing I want to construct or prove. This means that the primitives are part of the TCV, unlike coq. But it's for efficiency reasons, it's really important that we don't have to retype check proofs. Otherwise, the type extension would not really be that helpful in proof performance. So one of the things I really want to show you is the way we embed meta programs into FSTAR is FSTAR is effectful and actually has an effect extension mechanism. So I can define a monad just like in Haskell, and I get a new effect with the runtime semantics for it and the specification principle for it. So the way we define tactics is basically a state passing representation over a proof state, which is the set of goals that are open and we need to prove. It's easy to define as, it's basically this representation of proof state into an error or the value in a proof state. And if I return a bind, I do this magic invocation and I get a new effect into a start. And we can also relate it to existing effects such as divergence. This effect, we don't mark it total, so we can easily build meta programs can diverge. That's not a problem because they run at type checking time, and also all code that handles that uses exceptions can be lifted into the meta program port. And the state can only be modified by the primitives that we provide. Using the effect has advantages that meta programs are written as any other kind of program. They have nothing special in a start. You can define this thing. It's just a bigger style. It looks like just like standard ML. You can define high order combinators. You can use exceptions and catch them, and call into existing pure code, divergent, possibly divergent code, and possibly exception-tracing code, all of that from meta start or meta. Another cool thing that we can do is another entry point actually is we can use meta start to provide strategies for resolution of implicit arguments. So in this toy function, I'm defining the diagonal function. It takes an x and takes y as an implicit, but I give it the meta program to solve it in case unification couldn't solve it, and say, yeah, it's the same as x, and that's defined. This allows it to have a default argument. So if I write diag 42, I get 42. I give it explicitly, I get something else. And that's amazing, right? I know. So let's to kick it up a notch, because this is really not interesting. We also use them to implement type classes. With that same idea, instead of defining it as to return 42 or whatever, we actually define a class, a function tcresolve to do the instantiation of the dictionary automatically. And it looks over the program context to find all of the instances and compose them and do some search on them. And really, type classes in star are quite a feature, but they really have nothing in, there's nothing primitive about them except syntax. The only thing we have is like this funny braces there and the instance and class keywords that are just sure for some other thing that was written there. And the search for dictionaries, the tactic that does dictionary instantiation, fits in a slug. It's really just this thing. So it's really, we get type classes really for cheap. And they should really wrap up, I guess. Well. All right. Yes, maybe last thing. One of the advantages also of using an effect, just staying in the world of XStar, is that XStar can extract to a camel and compile and run efficiently. So we can also do that for meta programs as well. And yes, we can also do that for meta programs as well. So, and then once with the compiled meta program, we can actually link it back into the running XStar process and have a fast version of it. So the way this usually works is, for any XStar program, in particular with the XStar compiler, which is with XStar, we first extract it to a camel and then compile a binary for it. And here we have this. And now if I add some meta program, I can write a tactic, it's an XStar file, I can extract it and compile it, I get a dynamic object, we can link it back into a star, and this actually extends the normalizer, extends the interpreter with a new step. And instead of trying to interpret the tactic as a state passing computation, we just call into this function in the object we imported. And this really makes an amazing game speed, maybe 10x, and that's the average we've seen. And the fun bit about that is that it's not meta program specific at all. Any kind of function that you have in a star, you can extract it and link it back, and when you need to interpret it, you can just call into the thing and come back. At type checking time. In particular, we do this for type resolution, which means we can extend the compiler with a feature like type classes with really not a lot of performance penalty for it, and still keep it outside of the TC because it's guaranteed to be safe by the fact that it's a meta program that everyone cannot do anything that's bad, and so compiling and linking it back is not really increase the TCV. So, summary at the end, meta star we needed it to provide not only automation as many other proof assistants need tactics engine for automation, we also need it for control because we do not have access to the whole of the proofs data. We could not write proofs efficiently without it. Using an effect for meta programs increases reuse. We stayed within the confines of our language. Native compilation, as we just seen, allows us to extend the compiler with new primitives fast and safely, and we're using it to implement many new things in FStar that were previously out of scope, like doing separation of attributes of the sort. And yeah, it's still a work in progress. There's still things we want to do. But that's about it for now, I guess. So thanks for listening. I'm happy to take any questions.
All right, I think we have a time for like one quick question.
Yeah.
Go ahead.
So you said that before tactics, it was hard to write code that was stable with respect to the solver. tactics have improved that. My question is, how do you test for this kind of stability property when you are working?
Yes. Yes. One of the mundane ways of testing that is changing the solver's random seed. And you just take 100 of them, and if the thing doesn't succeed in 100, it's probably and it's really a market like for the example with models, I think you simply never see it succeed. Or maybe once in 100 seeds. And there's other ways, like try to open a module which adds more things to the content.
So is it something you do on a regular basis in the project?
No, not really. We also have a way, we have a thing called hints, where the SMT, when it proves something, it tells you which facts it actually used. And then we keep that, and when we try to replay a proof that was already done, we first try with those facts. And that's usually much more stable than this. Yes?
All right.
Sorry.
Very quick.
I'm sorry.
Can you how is it easy to write the tactical notation if you don't know how the actual encoding into SMT is?
Right. No. So you don't need to see the encoding.
No, you don't.
Okay. Well, you're right.
How is it easy to actually write it without?
Right. So you get to see it. I should have shown the interactivity. You get to see it if you run it and see that you can see the mistake when you need to prove. It's just not like Coq where you can stop it at any point. But in any case, one of the main use cases for this is more like hammer-like tactics, because the SMT for like proving formulas like instantiating and all that, the SMT is already excellent at that. I think you should say. But say for doing nonlinear arithmetic, it's just awful. And if you just take those equalities and canonicalize them, and that's all you do, writing the canonicalizer is not that hard. Then it's easier.
All right. Let's thank Guido again.